All right, so our last topic for the semester, congratulations, we've arrived at the last topic, is structure from motion, also known as, well, it's related to photogrammetry. And so we'll talk about kind of what those two things are. And I am using slides from UNAVCO, and this is a group funded by NASA and NSF. They're out of Boulder, actually. And they do a lot of cool stuff related to mapping the Earth in 3 dimensions and high resolution, especially when it relates to geology and geodesy. And geodesy is, again, is the study of positions on the planet. So Catherine Gervais gets credit for making this presentation, and I've done some light touches. So today we will define and explore structure from motion, theory and practice, and then we'll utilize SFM, structure from motion, to develop 3D models for civil engineering applications. So photogrammetry is the kind of method that we're using. And the idea of photogrammetry is that you can use many images. In this case, we have a stereo pair of images, 2 images, slightly offset, kind of like our eyes work, right? Our eyes give us essentially 2-dimensional images of the world. They're slightly offset, different angles. And because of that offsetedness, we get, our brain is basically doing structure from motion. It's pretty wild. And what this gentleman is doing is he's got these 2 aerial images where they have taken from an airplane at different, slightly offset angles. And maybe you've had a chance, like in an antique store or some sort of gift shop, to look through these kind of stereo images and see how it creates a 3D image. Very similar to how we have 3D movies, right? The movie has 2 images that are offset, and we wear these glasses that bring them together for our brain to get that depth of perception. So what this gentleman is doing is looking at 2 images, and he's tracing contour lines based off of some methods in photogrammetry that allows you to basically identify areas of equal elevation. And so from these images, these stereo images, we got the first USGS topo maps. And in fact, much of the 3D models for our nation, like that 10-meter digital elevation model, came from these. People digitized these topo lines and then made a 10 by 10 meter raster from them. And this, of course, is the Grand Mesa, and we've been looking at this little watershed, Canna Creek. Interesting. I guess this is Canna Creek. Anyway, this is Whitewater Creek, but yeah, so that's how it happens. And they did this for the whole country. And so photogrammetry, again, is taking images from different angles and using a method to interpolate and identify areas of equal elevation and create a 3D model from that. Nowadays, we have digital photography, and we have computers like my laptop, which can do the processing using really cool algorithms and kind of computer vision technology to build a 3D model for multiple images. So now, instead of a stereo pair, we can have thousands or hundreds of pictures taken at different angles, different elevations, and of an object. The way it works, kind of from a conceptual level, is that the computer software takes images that overlap. So you have to have overlapping images. And if this is the thing we're taking a picture of, these are points that are the same in these images. So we have to have a lot of overlap. So, somewhere around 50 to 70% overlap. And what it does is it's able to identify patterns and points and essentially pixels that are common to different images. And by identifying that and knowing the angle, elevation of the camera, if we think about a camera on a drone, we can know the elevation, the angle, the XYZ to, plus or minus 10 meters if we have a GPS on the drone. Then we're able to get a pretty good idea of where all the pictures are in space, and then where the points overlap each other. From there, you're able to get some distance measurements, the distance above the ground or to the ground to those points. So there's a lot of steps involved, and we're not going to pick apart everything, but I just want to give you guys kind of a brief overview of how this works. So here's an image that someone took from a drone of a fault line. So this is the faults in the ground from earthquake activity, tectonic activity. It took 500 photographs over 2 hours. They had a blimp that they had a camera tied to, and the camera just taking pictures every minute or sorry, every couple seconds. The original computer software or kind of code that was written came in 1999. David G. Lowe is the author of this, and it's called Distinctive Image Features from Scale Invariant Key Points. And so that's where this all came from. And so it's been in development and kind of been iterating for over 20 years now. There's a lot of ways we can create 3D models. And we've talked about LiDAR, which is a laser scan from an airplane or a drone. We can also have terrestrial LiDAR, which is the same technology just on a tripod. That's pretty cool, actually. And people do this. People do this to measure the slow deformation of landslides and stuff like that. And then structure from motion is photography. So we're not taking a 3D scan, with a laser pulse. Rather, we're taking images. In this case, it shows a blimp, but often people are using drones these days. All right, so let's just look a little bit more about the process. So say we have an aerial platform like a drone or a blimp. We have a camera on it. The camera has different angles, and we're able to, if you have a gimbal, which is a device that can rotate the camera in different angles, we can know that angle relative to the perpendicular. And then we can also get an estimate of X, Y, and Z from a GPS unit on board. So those cameras are taking pictures of the grounds, and they're looking for matching corresponding features or pixels in the image. So this scale invariant feature transformation, that's the computer algorithm, is key to matching these corresponding features. So that's the kind of computer vision elements to the software that's able to align and find matching pixels and matching patterns. So this is what that might look like. Here's an image from different elevations and different angles. And the software can find a little divot in the ground next to a bush, right? This little shadow thing, and it's able to find those from different angles and match those points up. And the idea of scale invariant is that it doesn't matter how close or far you are, it can still find those same patterns. So now that you've matched the locations in the software, there's usually one mathematical solution for where these two overlapping images were taken. So basically we find these 2 points, the angle, and then you basically do some fancy geometry to find exactly where those pictures were taken in space. And so if you know where those pictures were taken in space, then you can identify the distance between those 2 points in XYZ space. And so while we might not know precisely the real scale of it, right? It could be 10 feet or 10 miles, but we know the relative distance among all the points based on that solution. Now you put all those together and you create a dense point cloud. So we can do that with millions of points and create a point cloud of a 3D surface based on all of that. And those points have colors, right? And so we can create basically a 3D image and a model of that. The last step is what's called georectification, and you guys did that with 2 dimensions, right? You identified points in space. We had a reference image where we had known locations for a tree or a road intersection or something like that. And then you can basically stretch, scale, rotate your 3D model to match the true dimensions of it. And that's with what's called ground control points. And so ground control points, or GCPs, are images. And maybe we remember I was out there spray painting a circle and then we surveyed it, right? So those ground control points can be picked up by a drone or whatever image platform you have. And then by plugging in the XYZ for all those ground control points, with a GPS survey or something like that, we can then use the software to stretch the and scale the image so that, or the 3D model so that it actually fits real world dimensions. Finally, once you've got that model scaled and representing actual real world dimensions, you can create things like a digital surface model or digital elevation model. You can also create Ortho Mosaic imagery, so imagery that is basically corrected for the differences in elevation. So a lot of aerial imagery is what's called ortho-rectified and rectified by a 3D surface, and we'll talk about that later. We can also use texture mapping, and texture mapping refers to putting the images, a texture, basically stretching them over the 3D model surface. And so people use this in a lot of cool ways to represent things like ancient architecture, or as well as just buildings that we might be building. So what we're looking at is the overlap of photos taken of this particular scene, and the points are the center of each image. The colors represent how much overlap we have, how many photos overlap. And so you can see that we have a lot of dense information in the middle, and then we have very little overlap on the edge. And so the edge is going to have more uncertainty and kind of less information. So there's the Ortho Mosaic where we mosaicked the aerial imagery together, and there's a hillshade showing the 3D model that was created from it. And you can see there's that fault that they're trying to map right going through right the middle of the image. So as I said, there's a lot of platforms. We have drones, which we'll get to use, I think next week. And we have people will take pictures on poles, balloons. There's a lot of different ways to do it. You can just do it by hand. And actually that's your first assignment, is to do a 3D model of something, some objects, a car, a building, it could be your laptop, something that you can take pictures all the way around, and then make a basic 3D model of that. These little symbols right here are ground control points, and they're actually kind of like barcodes as well. And so the software, if we do this, can recognize these as a certain code. I tried that last year, and the resolution wasn't good enough to really have that work. So we might do a different, just a more manual way. So here's some geologists mapping with a pole, a camera on a pole. Here's a blimp. It's kind of cool. And here's a drone. So let's talk about how, first I'll say any questions about this. That was a real brief overview of how this all works. I'll also share with you guys some more reading materials about it. All right, so I'll just kind of show you a kind of a bit of a workflow for how we generate 3D models using structure for motion. You may or may not recognize this. Anyone recognize this building here? Might walk by it often. They actually just fenced it off this year. This is a little Xcel Energy utility shack between our Confluence Hall and Texas Avenue, so behind the parking lot. So I just went out there last year and took a bunch of pictures of it. I didn't get the tops. I just took pictures with my phone around it. I got about 50-something pictures there. Then if I wanted to scale this to the real world and actually give it coordinates, XYZ coordinates, I could have included some ground control points that I surveyed, right? So that should be in the image. So what the software will do is, and it's actually really straightforward in the software, is to step one, align the photos. And so what it does is the photos, in this case, they don't have any georeference. I just took it from my phone, right? So there's no, the software doesn't know where these pictures are in space. But what it can do is run that algorithm together or with all the pictures and basically find the pictures that overlap and then put them in space. And so what you're seeing is these little planes here are all the images with their orientation and their location of where I took the pictures, where basically my camera, cell phone was. And then you can see all these little points. These are the points that identified as common among those images. So I'm just showing you some different perspectives of that. As you can see, there's like the building envelope itself, and then you can see a lot of common points on the ground. And then it kind of thinks that maybe found some points in the sky. You end up deleting those because that's a little spurious. So it aligns the photos, and then the next step is to generate a point cloud. So we start with thousands of common points, and then it goes back and refines that to generate, you know, hundreds of thousands or millions of common points. After those points are generated, then you create what's known as a mesh. So this is very similar from the LiDAR workflow that we did. You start off with hundreds of thousands or millions of LiDAR points, and then we created a tin, or a triangulated irregular network. That's a mesh. A tin is a mesh. And so a mesh is a continuous surface connecting all those points. We might filter the points, and that's a step that's sometimes important to take, because we don't need you know, 1,000 points over the surface of one cinder block, right? So we can filter the points out to say, okay, if the points are kind of close enough, we'll take them out, and then our mesh ends up being a lot smaller in size. I did not filter this, and you can see there's a lot of like dimples and noise in the image, and filtering can reduce that noise as well. You can also see there's some sky that generated as a mesh. There's a way to delete those points that you end up not having that. As you can see, where we don't have a lot of overlapping images, for example, underneath this solar panel or behind these tires, you don't have any information, and so it kind of smooths through it. It just connects the dots across it. Similar to where on LiDAR, we didn't have information of the water, and so the tin just stretched across the water surface. So where that matters, then you have to take pictures, you know, from underneath, from different angles to capture all sides of it. But maybe it doesn't matter. Here's what registering ground control points might look like. Here, someone put a big X in the ground. They actually do this for LiDAR. They will create a reflective, an infrared reflective X on the ground, and then they'll survey that in the middle. And so they'll put those across, for example, when they did Mesa County, they have to do that across the whole county. Here's what it might look like from a drone. So the drone flew across this landscape and took, you know, a gridded series of pictures, and then they went over here and took a bunch of oblique pictures. Those are the flight paths. And there's different, we'll talk about drone, doing this from a drone. Might be, I think we'll talk about that, yeah, on Wednesday. But with drones, and as you know, we want pictures from different angles. And so here they're showing drone pictures, which are essentially perpendicular to the ground. When you want to do a 3D photogrammetry survey from a drone, what you end up doing is it'll do kind of a crisscross. It'll go in one direction like this, and take oblique images, so at an angle, and then I'll do another way and take another set of oblique images. So you get pictures with different angles, not just from this top. And so there's a landscape model, so you can create a model of, you can imagine a construction site, there's no vegetation. You could get a 3D model pretty quickly with drone imagery. And however, where there's vegetation, as you can see, there's some trees here. The imagery is just going to give you the top of that. There's no LiDAR that can penetrate down through the leaves with photogrammetry. It just gives you everything on the surface. So that's one of the drawbacks. Someone did an image of a rock sample, and they had little tiny targets. So you can do tiny models, or you can do big models. And then here's an example from civil engineering. So we had a dam that was being inspected. They had a drone fly all over to take images of this. And what they did is they did a drone image and created a 3D model from photogrammetry, and just kind of looked at these applications. So they put some targets in there where they drilled and took some concrete away, and then they put some 3D targets here as well. And they knew the measurements of those, and they wanted to see how well the aerial photogrammetry 3D model could recreate some of these things, some of these features. It ended up working pretty well. You know, when you have exposed beams and concrete, you can get pretty high resolution models of this. And so you'd imagine like a bridge inspection, for example, we can identify where we have pawing or concrete that's wasting away, and then we can measure the volume of that and figure out, you could even run, in this case, it created a finite element model to look at the structural integrity of this based on that missing chunk of concrete. All right, so there's some limitations of structure from motion. Reflective surfaces do not work. And so here's where they try to do a Swiss Army knife, where it's got a pretty shiny surface. That ended up not creating a very good 3D model because it's so smooth. You weren't able to find matching points. You need texture. So the wood is pretty good because you can find texture, but where you don't have texture, like water surfaces, mirrored surfaces, windows, you're not going to be able to connect the dots essentially, or find those common dots. Also, as I said, we cannot quote unquote see through vegetation. LiDAR can actually penetrate through leaves. It doesn't go through the leaves, but there's enough spaces between leaves that the laser can go down and come back up. So obviously vegetation is going to be limited. This is a structure from motion image of a forest. So if you kind of get in there and get enough images, you can get some kind of model, but it's going to be limited and all the dots won't be connected necessarily. It's hard to remove vegetation. There are methods and additional algorithms and software that you can use to identify vegetation points and remove that from the surface, similar to LiDAR methods. But it can be challenging, and if you don't have that more sophisticated software or the workflow associated with it, then you end up with 3D models that have vegetation in them, which isn't the end of the world all the time, but sometimes it's problematic. Here is a manuscript by Luke Javernak. He actually works in Colorado now, and where he did photogrammetry of a braided river. And he was able to create in GIS, a GIS workflow to identify vegetation and remove that from the digital elevation model. Okay. Great. So next time we'll talk about a little bit more about the workflow and how to plan a survey that we're going to do from a drone. So we'll talk about more of that considerations and stuff that we need to do for that. Do you guys have any questions about structure from motion? I'm going to give you guys a reading where you can dig a little bit more into how that computer algorithm works. I just didn't think it was super important to talk about in a lecture, but if you want to dig into those details, I'll have those resources on Canvas for you. Okay, I had Metashape running, but then let's see what happened. Metashape. All right. I was trying to process this in the background, but it restarted on me. So I'm going to walk you guys through a basic workflow. And if you want to open Metashape, you can follow along. We can download, let's see here. We can go on Canvas under assignments, and I'm going to publish this. It's called, I'm going to edit it super quick, lab. Okay, so it's published in assignments, homework, and labs on Canvas. Structure from motion 3D model. And then, let's see here, where is that data? I think if we go to modules, it's there. Okay, under modules, there is a structure from motion module. All right, and let's see here. So under the week 13 structure from motion module, we have the building photos zip file, so download that. And then we have the first tutorial is the 3D model tutorial. You can, for the assignment, you can follow along with that. That's from Metashape, they put this together, and it gives you the basic steps to create a 3D model. So that'll be your reference for later, but I'll do a quick walkthrough right now. But so download these photos and unzip them and pull up Metashape. And I'll give you guys a couple minutes to get there. I'm going to do a new project and I'm going to save as. It'll create a folder in documents. Let's see, is there a Metashape folder? So after I created a new project, file new, and then saved it in a location, I went to the workflow tab and I added a folder of photos that were all missing photos. And the first step I'll take is just align photos. And that does that really important step that was in that paper that I referenced from 1999 that figures out all those common points and where the locations of the actual images, where the lens was when the photo was taken. So there's some options you can do here. You can do different accuracy. So basically how fast will the algorithm run? We're going to leave the defaults in here for now. And this step actually happens pretty quickly. So now it's running that scale invariant, I'm not gonna remember the whole name, computer algorithm. And under those settings, you can basically say how many points do I want to try to match. And what I think it does is it'll either randomly or maybe there's a way that it optimizes what points it wants to match. And so it only tries for each image, in this case, 40,000 points for image to try to match. And so there's kind of like a limit. But you could imagine, you know, a 12 megapixel image has 12 million pixels in it. So there's 12 million potential options for matching points. So it's got to do a subset of those to align the images.
So where do I go? Where do I go to match the points?
Okay, so workflow.
Mm-hmm.
And then it'll say align. Once you bring the photos in,
yeah,
workflow align photos.
Okay. Thanks.
Now that we've done the rough image alignment where we did about, it said about 50,000 points to align these images, the next step in the software is to go back and look at all the pixels. So if I have 10 megapixel images, I have the potential for 10 million points that I can try to match up per image. So we go to workflow. We already did align photos, and now we're just going to do build dense cloud. You can choose the quality, meaning how many of those pixels we want to use. Do we want to use all of them or just do a sample of them again? I'm gonna stick to medium, and then we can say how much texture do we want in terms of depth filtering. And so if I want to do no depth filtering, I'm going to use all the points and I can have really fine texture. Or if I don't really care that much about texture, I can do more moderate or aggressive depth filtering. Again, this step takes a lot longer to do. So I've pulled up the Agisoft or Metashapes tutorial for creating 3D models. And they give you some more steps here in terms of setting things up. So we added the photos already. There's a step you can take to mask photos. That is if you want to basically get rid of anything in the background. It's a little bit of a cumbersome step. They do have kind of intelligent masking tools that can find the image and separate it from the background. Similar to when you do zoom and put in a picture in your background, there's algorithms that can figure out what's close and what's far. So you can do that if you're going to create a model of, like in this case, they did a little doll and they wanted to get rid of the background. We've already done the align photos point. And then you can set a bounding box. So once you've done that alignment, you can go to this tool right here where the hand is in the flat area, and you can adjust the box around the domain you want to actually have your model. So if you set it so that you basically just get the top of the building and you don't get anything in the clouds or trees or ground around that, you can kind of reduce the size of your model to where you only care about working. And that's using this tool right here. Now we started the build dense point cloud step. Again, we have different options. The quality is basically how long it's going to take and how many points we want to include. Depth filtering is how many, how detailed do you want that model to be. You can kind of smooth over the texture and kind of 3D variation in your model. This also reduces noise if you do more depth filtering. A new feature that's not on this is calculating the uncertainty for each point. And so that's an option you can check. It's going to run, a statistical algorithm to tell you the certainty in XYZ of each point. We didn't check that for this time. Once you've done that dense point cloud, and again, that takes a while. Let's see how we're doing on progress here. We're not quite halfway through. You get, essentially hundreds of thousands or even millions of points, depending on how big your model is. The next step is to build a mesh. What we might do before that, though, is we might filter the points out. We're going to do a model of Confluence Hall, and after running that a couple different times last semester, last time I taught this class, we found that we could filter the points out quite a bit. And by filtering points out, if you think about having, say, 10,000 points along a straight line, like the roof of a building or a straight surface, everything's pretty flat. There's not a lot of variation three-dimensionally. You can filter a lot of points out by saying, okay, if they're not going to change that much in elevation across this distance, then we can remove those. We don't need that information. Just like when you guys surveyed the creek or the slough out at Las Colonias, we don't need points along the flat plane of the bank. We can just get those break lines, right? So it's the same idea here. You can filter those points out, and by doing that, you have less information that you need to connect. So when we build a mesh, we're connecting all those points, that point cloud together. If we have less points, then the mesh takes less time to generate and it takes less disk space. These files can get very big because we're talking about hundreds of thousands and millions of points. Just like LiDAR data is really a lot of disk space. So you can save some memory there. There's a lot of different options you can have in terms of the resolution of your mesh. And so that's what this looks like. We now have a continuous surface, whereas here we were looking at a dense point cloud. So these are, it almost looks like a continuous surface. There's so many points, but these are really just individual points with colors associated with them. And then here's your mesh, which is an actual continuous surface. Kind of looks like a hill shade image, right? Another step we can take is to build the texture, and this is what assigns colors to each of these faces on the mesh. And if you guys ever do 3D video games, this is kind of like the same technique where you might create a 3D surface or a 3D world for a video game, and then you have to go back and assign colors and texture to that. Once you've done that texture step, you now have a full 3D model with all the kind of, you know, colors that came from the images you took. And now you've got a 3D model. You can export that model in different formats. And for this assignment, I'm going to have you guys try to export it to a website that hosts 3D models. And so you can kind of, you know, it's like uploading a video to YouTube. Instead of sharing the actual video, or in this case, a 3D model, you can share a link, and that video, in this case, a 3D model, is hosted on the website. It's called Sketchfab. There's a way to upload it through the software directly. Our students did not have luck doing that last semester, and so you can do it manually as well through the website. And that is the basic workflow. Let's see how we're doing over here. Looks like I was able to create that dense point cloud. So I'm going to click on that. I'm going to try to get my cameras not showing. Let's see. There we go. So this camera icon right here, if you guys take a second to look at Metashape, you have a camera icon. You can click on that to add the cameras or get rid of the cameras. You can also show the thumbnail, the actual image from that. All right, so now we've got our 3D model. I'm gonna zoom out a little bit and try to get this. Let's go to view, reset view. There we go. And this is not a mesh. It almost looks like a mesh, but if you zoom in, you can kind of see those points, right? So it's not quite a perfect, you know, it's not a continuous surface, but if you zoom out, it kind of looks like a continuous surface. All right, one of the steps we can take is to actually take out some of the points that we don't need. And I'm gonna do that. If you look at this rectangle right here next to the cursor, this is a selection tool. And you've got different tools. You can do a free-form selection, a circle, or a rectangle. I'm gonna try the rectangle. And what it does is it basically says, if this rectangle is 2 dimensions, it's gonna take everything kind of in that view and select those points. I'm gonna go back to my cursor, and then let's see what I did here. So it selects all those points in the view. And so I'm gonna do all these blue ones because I don't want the sky, that's not a real thing. So what I can do is zoom in, select those points, it'll give them a different color. And then I just press delete and they go away. I'm gonna try to rotate this so it's actually flat for me. Go back to my selection tool and try to get rid of all those sky ones. You can do freeform as well. Let's try that one. So I'm using the freeform tool now. Doesn't have to be perfect, but we'll just do a little bit of work here to and then yeah. Go ahead.
Are you just like deleting those points, or was
yeah,
it
like... I did the select, and then I drew around them to select them, and then I just do delete and they go away. You can also do Control Z if you want them to come back. Control Y and Control Z work if you didn't like that selection. So I'm going to select something, and then I think if I just do escape, no. If I select something and I don't like what I selected, I can just click outside of it and it'll get rid of that selection. There's some weird tree stuff going on here. And remember, if you want to get a different view, if you want to pan the image, you can click on that pyramid and you can really just drag and zoom where you want to. So see how I selected, it got behind in the wall behind me. So make sure you get the view right. You can bring that ball back by going over to the cursor, and that little magic ball comes up, and then you can change the view vantage point just to get that sky. I'm going to get rid of that fence. I don't like that fence. We don't need it. There's a little gate and fence over on this back corner here. I see some points floating in space over here. Now that we've cleaned it up pretty well, just take a look, do a little tour. You know, we got rid of a lot of the sky stuff. We got rid of that fence that was sitting back here. So we have mostly just the building. We have those tires. That's cool, whatever. We'll keep the tires. We can filter the points. So if I go to Tools, Dense Cloud, Filter Dense Cloud. And what it says is, what do you want your point spacing to be? So, you know, you can go through here and just say, okay, I want a point every, in this case, it says every centimeter. So 0.01, that's the current, or sorry, it gives you the current point spacing on average. So you can say, okay, what do I want my actual point spacing to be? Every centimeter, maybe let's do every point. Whatever, we'll keep it as 1 centimeter. That's not a huge file. So 0.01 meters is 1 centimeter. Do you want to replace the dense cloud? Yes. So it's going to take a minute to filter those points out. Maybe you could do 2 centimeters. I don't know. It's a pretty small building. If we were doing Confluence Hall, maybe we could do every 10 centimeters or something like that. All right, if we zoom in now, we can see that the points are pretty evenly spaced. So we took some of the points out. We could have gone even more if we wanted to, but decided not to. Okay. The last step that we'll talk about now before we break is we go back to workflow, and then we can build the mesh. So now that we've done a little filtering of the points, you could have filtered more if you cared to. You can choose which source data you want. That's going to be the dense cloud. That's 6 million points. The points actually increased when we did that filter, so I don't know if that was the best idea. We'll keep arbitrary 3D. That just means it's going to connect all your points together. And then how many faces do you want? It says, okay, you could have 1 million faces, you could have 400,000 faces. We'll just keep the face count high because it's a small model. And then we'll just keep all the other defaults and we'll run that. This one takes, I think, a lot longer. It should take than the dense point cloud. So you can run that now or you can run it later, doesn't matter. If you want to save it to run, overnight or something like that, maybe it might take an hour or two, I'm not quite sure, but it would take a little while, especially on a laptop. So because we're at the end of class, you don't need to run that right now. Once you do that, we will go through the remaining steps in the Metashape tutorial, which is to generate that mesh, build the texture, and then you'll export your model. All right, guys, you are pros at this. What I'll have you do for this assignment, though, is I'd like you to do your own model with your own photos, just so you think about how you do that. I included these kind of for the class exercise, just to give you the steps and kind of show you what it looks like. So that can be anything from a car, although note that shiny surfaces don't do well. It could be a tree, it could be a bush, a bench, your laptop. So pick something that you can get all angles of and do a model. Maybe it's just your desktop or something like that. So that'll be for the assignment is take your own pictures. I'm going to continue building this mesh. And you basically just follow through those steps and there's a document on Canvas for how to write it up.